So here's its Maclaurin series. Let's start plugging in values of n. So start with n is 0. What do you get when n is 0? This is 1, 1, and 1, right? So you get 1. So we get integrating 1 plus. Now, replace n with 1. And what do you get? Oh, it's not going to be plus. It's going to be what? Minus 1 factorial is 1. So minus x squared. Next one's going to be plus, right? When we replace n with 2, negative 1 squared is 1. 2 factorial on the bottom, x to the 4th. I'm plugging in 2. So 1 over 2 factorial x to the 4th. Next one should be minus, shouldn't it? Minus 1 over, where are we at? 3 factorial x to the 6th. Next one should be plus. 1 over 4 factorial x to the 8th. Next one, 1 over 5 factorial x to the 10th plus dot, 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 close it off, dx. Right? Now we know that the infinite series here is equivalent to e to the negative x squared, and this is where we were talking about how precise do you want to be, right? So if I rewrite this, equals, let's find the antiderivative term by term. What's the antiderivative of, oh, and yeah, well, we have to have a plus c out here, don't we? Now, it's weird to do a plus c at the end of dot, dot, dots. So a lot of times when we do integration of power series, we put the plus c out front. It's a constant plus. Now, oh, but this is a definite integral. Hold on. This is a definite integral. We don't need the c. We don't need the c. All right, antiderivative of 1. X. You know what? I'll go up there. I'm being lazy. I'll go up here. So the antiderivative of 1 is x. And then minus what? 1/3 x cubed. Okay, now this is going to get weird, all right? But let's just do it. This is going to be plus 1 over 5 times 2 factorial x to the 5th. So I just did the power rule, and I carried the factorial with me, right?
So you just treat it as a constant?
Treat it like a constant, yep. So this one, I'm going to have a 1/7 x to the 7th, right, from this? But I'm just going to put it next to that. So minus 1 over 7 times 3 factorial x to the 7th. And I can just keep going, right? Plus 1 over 9 times 4 factorial x to the 9th. One more. 1 over 11 times 5 factorial x to the 11th plus dot, 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 right? And then evaluated 0 to 1. Okay? Right? Now, plugging in 0 is really nice, isn't it? Because it kills everything off. So really all I need to do is plug 1 into this. So what would happen if I plug in 1? And by the way, you're asking what's the general antiderivative? This is it, right here. Plus c, right? And then what you could try and do is find a pattern in that and write out a summation formula for it. Right? Okay, yeah. But I'm going to finish this off. If we plug in 1, we get 1 minus 1/3 plus, let's see, 2 factorial is 2, right? So that's just 10. Minus 1 over, let's see, 3 factorial is 3 times 2 times 1. So that's 6 times 7, which is 42. Plus, okay, 4 factorial, 24 times 9. Calculator, please. 24 times 9. What is it? 260? 216. Okay. And then what about the next one? Minus 11 times 5 times 4 is 20 times 6, 120.
1,320.
1,320, I believe me, 1,320, whatever, plus dot, 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 right? So we are back to like our old school, like just numeric series here. And this should converge to something. I mean, this should, now, you know how I was saying we could find the formula for this somehow? Like somehow try and rewrite this as sum, right? And we could ask ourselves, when does it converge, right? And do a ratio test. So if we go back, you see all these right here? We could have done a ratio test on all of these to try and figure out what your interval of convergence is. Now, I'll tell you what they are right now. Everything, all real numbers. I mean, sorry, every x. Negative infinity to infinity, this works. Negative infinity to infinity, this works. Negative infinity to infinity, this works. On the table, on page 484, it'll tell you what r is on the side. In other words, this formula is valid for all x. So if we put negative x squared in there, that's still a real number, so this is valid everywhere. So it's going to converge is what I'm getting at. This is going to converge to something. All right? All right. That's it. Now, Taylor series. We've done Maclaurin. Let's do Taylor. How do I want to start with Taylor? All right, so find the Taylor series for f of x equals e to the x at a equals 2. Good luck on your test. He's taking his driving test today. Good luck. No, I'm kidding.
Savage.
Brutal, right? You can do it. You can do that parallel parking. All right, so this is a big difference right here, right? This is a big difference because we are doing it about a, which means our formula changes. The formula we're going to use is that the function we're trying to rewrite is the sum n equals 0 to infinity. But now, instead of the nth derivative at 0, it's the nth derivative at what? A, so 2, right? I need to plug 2 in there. Nth derivative at 2 over n factorial x minus 2 to the n. See how the formula changed? So I'm still going to come over here and do a column, 2 columns. But as you're going to see, this is going to suck a little bit more, right? So the first derivative, right? The 0th derivative of this function at x is what? E to the x. That's still good, right? Yes? Well, you know what? This one's not going to be bad at all, now that I think about it. Yeah, this is a good first example. Because the first derivative is also e to the x, right? And then they're all the same, aren't they? And now when I plug in to find the 0th derivative at 2, what do I get? E squared, right? And that's going to be the same for all of these. Nothing changes. Y'all see what I'm saying? So how does that impact our summation? We know that this right here is always, we got lucky, is always e squared. So what we can say is that this power series is equal to, this Taylor series I should say, is e squared over n factorial x minus 2 to the n. That's it. This is kind of a trivial one. I don't like it, in fact. It's too basic. So let's try something a little harder. Maclaurin, e to the x. Okay. Let's try this one. Let's do f of x equals cosine x at a equals pi over 2. All right, our formula is going to be sum n equals 0 to infinity, the nth derivative at pi over 2 over n factorial x minus pi over 2 to the n. So that's your Taylor series, right? We still need to come up with figuring out what this is. The zeroth derivative of this function at x is cosine x. First derivative, negative sine. And then, can I keep going? Negative cosine x, right? Sine x, cosine x, and that's where it starts repeating itself. What's the zeroth derivative at pi over 2? Cosine of pi over 2? What is that? Pi over 2 is straight up. Cosine is the x-coordinate. 0. What is the first derivative at pi over 2? So what is sine of pi over 2? It's 1 and then negative, right? So negative 1. And then we're going to get 0 again. What's wrong? You all right? What? No.
Did you say negative 1?
Sine of pi over 2 is 1, but it's negative here. Did I? I said negative 1.
Yeah.
I didn't write negative 1. Okay.
Wilson just thought.
Yeah, I don't know. Okay. All right, the next one will be 0. The next one will be 1, then 0, then negative 1, 0, negative 1. Okay, so you get the idea here? Okay, let's keep going here. Let's write out the series then. It's going to be you tell me. 0 over 0 factorial x minus pi over 2 to the 0, right? So that's the first thing we get when we plug in 0 for n. We get that number over n factorial x minus a to the n. Plus, so yeah, it's plus, but it's going to be minus because of that. So minus, let's do plus negative 1 over, okay? It doesn't hurt. Over 1 factorial x minus pi over 2 to the first power. And the next one is 0, right? 0 over 2 factorial x minus pi over 2 squared.
Hey, I'm sorry.
Yes.
I know I stepped out. What is where did the x minus 5 3?
I said let's find the Taylor series for cosine x at pi over 2.
Okay.
So pi over 2 is now a. Instead of 0, Taylor series has x minus a.
From the definition of
Taylor series. You weren't quite here. Yeah. It was before I did Maclaurin, I did Taylor. But I said we're going to start with Maclaurin examples. Okay, so what's the next one? What's the next piece here? Plus, we're on the third one. So it's positive, right? 1 over 3 factorial x minus pi over 2 to the third. And I think you get the idea what's going on here. Okay. A bunch of these things are gone. All these zeros are gone. What would be the next one that actually matters? What would be our next term that actually does something? So plus negative 1 over 5 factorial x minus pi over 2 to the fifth. All right, let's see if we can't write this as a formula, as summation. Sum n equals 0 to infinity. It alternates, doesn't it? But where does it start? A negative. So now for this one, I do need negative 1 to the n plus 1 or minus 1 over. What are my factorials on the bottom? 1, 3, 5, right? So 2n plus 1 factorial. And then everything else, this is this thing to the 1, this thing cubed, this thing to the fifth. So x minus pi over 2 to the n. 2n plus 1, sorry. It's got to be odd powers. That's it, yeah, that's the power. This is the Taylor series. That's the Taylor series, yes. All right, we're going to do something. We're going to do something a little different. We're still in this section. Do something a little different here. I want us to try and find the Taylor series. I'm sorry. I want to go back to Maclaurin for a second. What's the Maclaurin series for this? I'm going to show you two ways to do this. The first way is going to be the hard way, but it is very instructive in terms of, well, you'll see. And then I'll show you the easy way, which is, well, easy. All right, here we go. So let's act like we do not have the Maclaurin series for sine. Let's say we don't have that, all right? Because this could very well be a function that is not on our table. Do you all see that this right here is just x times this, right? We know what that is as a Maclaurin series. So x, I would just be basically putting an x out in front of here and here, and just push the x into the formula, right? Okay, but let's act like we don't know that. So here's what we need to come up with. We need to come up with sum n equals 0 to infinity, the nth derivative at 0 over n factorial, x to the n, right? We're plugging in 0 because we're doing a Maclaurin. So I'm going to come up with my table over here. And this is going to be complicated. What is the 0th derivative? Well, that's just itself, right? Okay. What is the first derivative? Product rule, right? Product rule. So when I do a product rule on that, what do I get? Sine x plus x cosine x. Right? What is the second derivative? Cosine x plus another product rule. Cosine x minus x sine x. So I did derivative of this is this, product right here, derivative of that was 1 times that, and then derivative of that, which is negative sine x times that, that's this. Now before I take the derivative again, I'm going to clean this up. This is 2 cosine x minus x sine x. And we go again. What is the third derivative of this? All right, so that's going to become negative 2 sine x minus the derivative of x sine x, right? Which we already did, right? That's this. So I can just copy and paste this right here, right? but I have a negative sign. So the negative goes to here and here. So minus sine x minus x cosine x. Agree? Combine, this is negative 3 sine x minus x cosine x. What would the fourth derivative be? Not yet. Negative 3 cosine x, right? And then minus, now we have to take derivative of this, but we already did that, didn't we? That was right here. This one right here became this. Yes? But we're subtracting it, so it's going to be minus that plus that. So minus cosine x plus x sine x. So negative 4 cosine x plus x sine x. Okay, we may need to continue, but I think we're starting to establish a pattern here. Do you agree? All right, let's see if we can't figure out what happens to these as we plug in 0. Okay, what do we get when we plug 0 in? First one's 0. Okay, what about the first derivative at 0? So sine of 0 is 0, right? Then 0 again? So 0. Okay. What's the second derivative at 0? So that's the second derivative here. Cosine of 0 is 1, right? So we just get 2, and then this is 0. So we get 2. What's the third derivative at 0? 0, 0, so 0. Okay. What's the fourth derivative at 0? Just looks like negative 4, right? Do you have a pattern here? I don't know. Do you see a pattern? What do you think the next one's going to be?
0.
Okay. What do you think the next one after that's going to be?
6.
I think you're right, but we should double check just those next two, just to make sure. Because I think if we do that, we can assume that we've got a pattern here, right? Yes?
Yes.
Okay. So let's do the fifth derivative. Fifth derivative of x. It's not so bad, right? This right here becomes 5 sine x. And then plus x sine x. So we're back here, aren't we? Yeah. We're back here. So that's just going to be plus sine x plus x cosine x. So what's that? So this is going to be 6 sine x plus x cosine x. All right, so what would happen if we do the derivative? We may as well do it while we're here. Derivative at 0? 0, it's all gone. So 0, so that's what we thought it would be, right? Let's do one more. I'm just going to put it over here. The sixth derivative is going to be 6 cosine x, just like we thought, and then plus x cosine x, take its derivative. We did that right there. So cosine x minus x sine x. Oh, shit. Where did it come from? Oh, wait, yeah, hold on. This should be 4. Why didn't y'all say something earlier? Oh, you're trying to figure out. Okay, sorry. Yeah, I took derivative of this. I think I did get ahead of myself. Derivative of this should be what? 4. So change that to a 4. Sorry about that. And then this should be a 5. Which means this should be a 5. Which means it should be 6 cosine x minus x sine x. There we go. So when we plug into that, we get 6. So the sixth derivative at 0 is 6. And I think we can safely say the next one would be 0, then negative 8, and then 0, and then 10, and then, okay, yes? All right. Now, let's go ahead and start writing this out. So if I write this out, this sum, What was the zeroth derivative at 0? 0 over 0 factorial x to the 0. Plus, what was the first derivative at 0? 0 over 1 factorial x. Plus, next one, 2 over 2 factorial x squared. Plus, we can skip the 0. Do you want to skip the 0? Okay, so what's the next one then? Minus 4 over 4 factorial x to the 4th plus 6 over 6 factorial x to the 6th minus 8 over factorial x to the 8th. One more. 10 over 10 factorial x to the 10th plus. It would be a minus, but you got the idea, right? Okay, so now when we look at this, these first two terms aren't even here, right? Because they're zeros. And can we come up with a formula for that? What would it be? Sum n equals 0 to infinity. Oh yeah, and I want you all to see something here. This right here on the bottom, isn't that 2 times 1? And the 2's cancel. And you just get 1 on the bottom, right? Right here, this is 4 times 3 factorial on the bottom. The 4 and the 4 cancel. And then this is like 6 times 5 factorial. 6's cancel. Right? So 1 over, it's going to be, what are our factorials on the bottom going to be? 1 factorial, 3 factorial, 5 factorial, 7 factorial. And it alternates too, doesn't it? Negative 1 to the n. That'll start you positive. On the bottom, it's 2n. You want to start at what? At 1 factorial. So plus 1 because you're starting at n equals 0, right? So if I go n equals 0, that's 1. N equals 1, that's 3. You all right with that? It gives me my factorials on the bottom. And then x to the 2n. I want evens, don't I? Evens starting with 2, 4, 6, 8. So I want evens starting with 2. 2n plus 2. Agree? That's it.
If we hadn't noticed that they reduced like that,
You could have left it as negative 1 to the n. That would get your alternating. And then what would you have? 2n. It would be 2n plus 2. Because you would have to start, you're trying to start at 2, right? 2, 4, 6, 8. So it would be 2n plus 2 over 2n plus 2 factorial x to the 2n plus 2. You could do that, right? But now you could say 2n plus 2 times 2n plus 1 factorial. Cancel, cancel.
I think it's easier to see it like that.
It's easier to see it that way? Okay, whatever. Whatever. If you left it like this, without canceling, it wouldn't be wrong. But what I'm about to try and show you something now. This was the hard way, right?
Well, can't you just put the x?
That's what I'm saying. Yes, that's what I'm saying. This is the easy way. The easy way of doing that is to say, okay, x sine x is the same as x times the power series for sine, which is that. N equals 0 to infinity, negative 1 to the n times 1 over 2n plus 1 factorial x to the 2n plus 1, right? Yeah. So if I bring an x in here, the x is going to go right here next to this. And then that adds the exponents, you get 2n plus 2. So it would be this. Right? So if you know the power series for something, then you can combine it with other functions, power functions in, if you change that to cubed, right? Then the power series just changes, that number up there is going to change, right? I hope that makes sense.
If it were to be like some, I don't know, like 3/4 x squared of sine x, would you just push the 3/4 x squared?
3/4 x squared.
Like I'm just throwing an arbitrary.
3/4 x squared. Yeah, the 3/4 would just, are you saying what happens to the 3/4?
Like you would just put it through?
Yeah, you just put it out in front here.
Yeah.
Or you could even leave it out here. Okay, I want to do one more because I only have 10 minutes, and I just don't think I'm going to have any time to do anything out of 8.6. I want to find the Maclaurin series for, what do I want to do? Cosine of pi x. Now, again, I'm going to do this the easy way and the hard way. All right? The easy way would be to take pi x and put it right here in this formula. That would be the easy way. All right? But again, the reason I want to show you the hard way is because I think it's constructive in terms of working with factorials and things. All right? So watch. I'm going to go straight to the table. I need to find the 0th derivative at x. So what's the 0th derivative of that? Just itself, right? Pay attention here. What's the first derivative of this? Negative pi sine pi x. So because of chain rule, you're going to have a pi pop out, aren't you? Okay, what is the second derivative of this? Negative pi squared. Negative pi squared cosine pi x. So no product rule here, right? That's a constant. So it comes for the ride. Derivative of sine of pi x is cosine of pi x times pi. Third derivative.
So negatives cancel.
You'd have another negative, so it would become a positive pi cubed sine pi x. And maybe we'll just do another one or two of these. Fourth derivative, pi to the fourth cosine pi x. One more. Fifth derivative, negative pi to the fifth sine pi x. Now let's figure out what happens when we plug 0 into all of these. So the 0th derivative at 0 is cosine of 0? Okay. X1. First derivative at 0. Well, it's a sine function, isn't it? So it's gone. Okay. Next one. Negative pi squared. Because cosine of 0 is going to be 1. This one's going to be 0. This one's going to be pi to the fourth. This one's going to be 0. Next one. Negative pi to the sixth. 0, pi to the eighth. So we've established a pattern, haven't we? Okay. Except for the first ones. Not quite sure we have a pattern there, do we? Good. I'll say positive pi to the 0. This is actually pi to the 0, right? I can say that. So it's like positive pi to the 0, skip, negative pi squared, skip, pi to the fourth. So we got even powers and they're alternating. So if I wanted to, let's see how gung-ho you are here. Can you go straight to this without writing them all out? So it's going to go, you want it to alternate? Yeah, I'm just going to go straight to the formula. I'm not even going to write them all out. Negative 1 to the end, that'll take care of your alternating.
Then 1 over.
So you got to have n factorial on the bottom, right? You have to because it's a Maclaurin series, okay? It's always going to be there. And then what's this thing doing? We've got pi's to what powers? Even powers starting at 0. So how about pi to the 2n, like that? I'll just extend that out. Does that make sense? And x to the n. Don't forget x to the n, right? Or else it's not a Maclaurin series. So let's just check it. Does that work? If we plug in 0, we get a positive 1. We get pi to the 0, which is 1, and then we get 0 factorial, which is 1, and then we get x to the 0, which is 1. So our first piece would be 1. And then plus, well, actually, it's going to be minus now. Minus, and then it'll be pi squared over 2 factorial x squared. All right, that's what we would have got from this piece right here. And then the next one will be plus pi to the 4th over 4 factorial x to the 4th, so on and so forth. So that should do it. Now, could we have done that any easier?
Yes.
Yeah, the easier way would have been to take this formula right here, right? And just replace x with what? Pi x, right? Would that have worked? Because that formula looks way different, doesn't it? Yeah?
What the heck?
I've still got time. Let's try it the short way. Let's see if we can get our formulas to match. See if our formulas can match. So if I do, using that, cosine of pi x should be sum n equals 0 to infinity, negative 1 to the n, and then 1 over 2n factorial, and then pi x to the 2n, right? And if I split this off, I get pi to the 2n, that's that one, over 2n factorial, right? Did I do n factorial? I forgot my 2n factorial. I'm rushing. Sorry. This should have been 2n factorial. Because you needed evens, right? On the bottom? Golly, Robert. Do you understand what I'm saying? I needed evens on the bottom. Because we took out, we didn't write all the zeros. That's why writing it out's real good, because you can see where the zeros go away. You pick up all the evens. You have to pick up the evens, right? So I think we're there, right? This is it. X to the 2n. Did I not write down 2n here either? Shit. Okay, just throw it away, man. Throw it away. Maybe what we should have done is actually just wrote them all out and then turned it into the series. Yeah. That's the safest way to do it. All right. I'm trying to rush. All right. So where do we go from here? We still have a little bit more to do in this section. All right. We are going to learn how to take two power series and multiply them together, and how to take two power series and divide them. Okay, and that'll be the last thing we'll be able to do. And then I'm going to actually have to go back to 8.6 and do a couple of things in there. So that's where we are, okay?
Hey, are we still doing the Fourier transform thing?
I need to look at a time when that would work for me next week. Yeah, I know. All right, try to start your homework for this section.